So you need to build a chart inside a React application. Well, your first approach, as always, should just be to just use a library, right? For example, this Rechart is a very popular library. The title says, a composable charting library built on React components. It has a very beautiful API, is very declarative, and maybe this is just good enough for you, okay? As always, first try with a library and then start implementing your own solution. But maybe you have a design, a specific design that you need to implement, such as this one, for example. And maybe your design needs to have some complex, this chart needs to have some pretty complex interactions, such as this one, for example. Oh, yeah, explain. Okay, yeah, there is, sorry. Such as this one that has the tooltip, and it's a pretty complex tooltip. And maybe you need to put this chart in a PDF too, because why not, you know? Automated reports needs to have a chart, there you go. Or if you need to send an email with a report to the user, maybe you need to also put this chart inside. Yeah, I needed to do that. And that's built with tables. It's fascinating and horrifying at the same time. So how do you do that? I'm Alberto Restifo, I'm a full stack developer. I work at LangAI, where we are building an API for language understanding and intent extraction. And on top of our own API, we built Synthesis, which is a dashboard that brands use to analyze conversation in social media. And this year, I built many charts. Some of them are completely custom with a lot of nice animations, and they're used to demonstrate the capability of our API. Some of them are just gigantic. This is what used to analyze the result of the classifier for your data, and all those are built with. So the first approach you could use is to just use a ref attribute. It will go something like this. You maybe search for an example on D3 blocks or any other website where you have a pre-made example with D3. In this case, throughout our talk, whenever I reference some code with D3, I'm taking it from this example, a simple line chart. And you will do something like this. Inside your render, you render an empty SVG element where you put a ref attribute. And inside of our ref function, we are saving inside our component a reference to the SVG element. Then in component.mount, we instantiate D3 select, passing our SVG. And then we just put essentially the code that we copy paste from the D3. And this works. So thank you, right? Done, right? Oh, no, wait a second. What about those interactions? What if you need to add those interactions? Well, fine enough, you can just, for example, if our line chart has circles, you can just append an on-click listener to the circle, and if the data of your chart needs to change the response of this click event, you simply move your render function to its own place, call it from component. For this to work, there is a couple of things you should note. Of course, the render chart function needs to use the data from the props. Then the props data must be immutable, otherwise the function to check for updates can't be as simple as that. And the D3 logic inside of render chart needs to be able to be called multiple times and still render correctly the chart. Specifically, this last point is a little bit tricky depending on how complex your chart is. But I can deal with this. It's still fine, it's still manageable. So what about tooltips? What if you want to add a tooltip? Oh, when you need to put syntax highlight in your presentation, you know it's gonna get complex. So let's break this down. First, we're gonna somehow fabricate a div, maybe again a ref attribute in our render. Then for every one of our circles, we're gonna add mouse over event. In the mouse over event, we're gonna inline some HTML in the previous div using D3, pass some styling attributes, and then on mouse out. the title of this presentation is charting React the right way. So what is the right way? Well, we're going to take advantage of the fact that the D3 library has become very modular recently. So we're going to use the math functions from D3 to compute the complex parts of our charts. And then we're going to use simply React, plain old React, to draw out our SVG in the chart. So let's see how it works. This is what we will build throughout this demo, this chart with this nice animation. It's based on that example, and the line signifies my level of stress as the talk approaches. This is this morning where I start questioning half my slide. So let's see how we build this. First, we should know a couple of basic concepts about SVGs, just so we are on the same level. If we are creating an SVG element with a width of 500 pixels and a height of 500 pixels, the top left corner is going to be 0, 0. The bottom left corner is going to be 500, 500. However, do note that 500 does not necessarily mean 500 pixels. That depends on the view box that you're setting. If in our example, we have a width of 250 pixels by 250 pixels, but we pass a view box of 500 by 500, the bottom left corner is going to still be 500, 500, but its position is going to be 250 pixels, 250 pixels. Throughout this method, we are not going to specify a view box, and if you do not specify a view box, but you specify a size, they match perfectly. So, second thing, a couple of things about the group element, the G element. It's very simple, actually. It allows you to specify a property that is applied to all the children of the group. So in this example, we have two circles. We specify fill red, and sure enough, the result is 2 red circles. So it's just basically a shortcut to specify properties. Do not worry about the rest. The rest will be taken care of D3. Just one thing you should know is that you can add an emoji at the end of a path, and it's still a valid SVG path for some reason. So that's nice. So let's start by creating our SVG element for the chart. Again, this is the D3 code to do that, where we create a path, and then we append a group, and we apply a transform to that group. The reason why we apply the transform to that group is because it allows us to specify a margin in our chart, to add some margin around the actual chart, without affecting the coordinates. So 0, 0 is going to still be the top left corner, but we're moving the chart maybe 20 pixels on the right. That's the only purpose of this margin, of this translate, sorry. And if we want to do that in React, it's pretty straightforward. We just type out an SVG, pass in the width, the height, and the transform with the translate property. Same as before, nothing changed. It's just that now it's React. So then we need to start drawing the line for our chart. And this is the D3 code to do that. But first, let's see what this D3 line is doing. It comes from the D3 shape package. And I'm going to leave these methods explained the same way as you see them in the D3 documentation. And I'm doing that because I think it's an awful way to point out how a method works, but at least if you get familiar with it, it's going to be easier when you check out the D3 documentation. So the D3 line function returns you a new line generator with the default settings. And a line generator is an object that has these two methods, x and y, which you need to pass an accessor function that tells you from a given data how to find the x coordinate and how to find the y coordinate. Lastly, you can call the line generator. You can just call it, passing in the data, and you get back a string that is the correct path for your SVG line. And if we take a look again at the D3 code, that's exactly what's happening here. First, we are creating a line generator function. Then we are specifying x and y, the accessors. In this case, we are using two scales. One scale is on the date, and the other scale is on the value. The value is the value of stress. The date is the current day. And then the last thing is some kind of D3 magic where you just pass in the line and it knows what to do on its own. If you want to do this in React, it's pretty much the same. You create a line generator function. Afterwards, you create a path and you manually type out the properties of your path that before you were passing them in D3. And lastly, you manually invoke the line generator function with your data. And that works. It's as simple as that. And of course, you can always add your emoji at the end if you want. It still works. But we have a problem in this code, and the problem is here. This means that on every render, as you can see here, we are rescaling the data. And the problem is that this means that the renders becomes expensive. Every render has a lot of computation. And in React, your render function might be called multiple times, even if nothing changed. So to avoid this, we need to move our data to the state. And the way we're going to do this is by creating a set data function. And the first part you can ignore is just a standard D3 scaling for the X and Y axis. The interesting part is down here, where we are iterating the data we receive from the props, scaling it, and then setting it to the state. After we've done that, we need to set up our function to be called in component will mount and component will receive props. Don't worry too much if you get lost following the actual code. What I want you to learn from this is mostly the technique. The code is in this case an implementation detail to help explain the technique. And anyway, the slides and repository are all available with the code that you see here. Once we've done that, we need to do a small change in our render function, which is simply essentially simplify the accessor function in the D3 line generator. Now we don't need to scale the data anymore. And then to the line function, we pass the data from the state. So let's see some quick reason of why this is really awesome. First, if you have noticed, now we don't need the DOM anymore, right? Before with D3, we were calling our D3 function in component did mount, in component did update, because the D3 depends on the DOM being updated. This time we are not. We're calling our function in component will mount, in component will update, or component will receive props, whatever, React. So it means that now our chart can actually be rendered on the server, which allows you to say put it in a PDF or in an email. And then this time we're using the React super fast reconciliation algorithm, because React has its own implementation of the virtual DOM, D3 does not, so React is going to always be faster than D3 to update the actual DOM. And then lastly, we're getting super fast renders because there is no computation whatsoever in the render. It's just creating a simple SVG. So that's how I feel after this code, classically after the D3 example as before. But now this thing is going to get better, because let's add the points to our chart. This is how you do it in the D3 example. You select all points, pass in the data, and some D3 magic that allows you to iterate circles, essentially specifying radius, again, X and Y coordinates for the circle, and some styling. Fine. Let's try things a little bit differently this time and make our own React component. We're going to call it point. Our React component accepts two attributes, X and Y, and it just, surprise, surprise, renders a circle. Same property as before. Center is X and Y. The radius is 4. It's the same code as before. It's just that now we are typing it out in React. Once we've done that, it's as simple as going back in our line chart render function and iterating the data points and putting in the point element. So that works. What about the tooltip? That was my breaking point for the React example. Well, it gets even better. Let's create a simple tooltip component. In this case, I kept it minimal for the sake of the presentation, but it's just a React component. You can do whatever you want in here. In this case, I have the opacity which when the tooltip is hidden is going to be 0. When the tooltip is visible, it's going to be 1. And I'm setting its position to X and Y using transform. So it's going to be a more fluid change. Then, before we actually insert our tooltip in the render function, we need to do a little change here. We need to wrap our SVG element inside of a div. And in this div, we're going to specify the width to be the same width of the chart, the height to be the same height of the chart, and the position to relative. What it means that our SVG and the div have the exact same coordinate system. So the top left point of the div is going to be 0, 0. The top left point of the SVG is going to be 0, 0. And when to the tooltip we pass X and Y, it's already the correct X and Y for the line chart. Then we just add inside our div the tooltip, passing in whatever property you want. Here I'm not showing the logic to actually toggle the tooltip, but we will add to the point, we will add an on mouse over and on mouse enter callbacks, pass them to our line chart, and update the state. Let's look at the axis now, because this chart is still missing the axis. That's where we are a little bit more on our own, because there is a problem. The D3 functions to draw axes are a little bit too much magic, and they require a DOM, and they return a full-blown SVG that you can then insert in your chart. And this will not work for us. But with that said, there are some helpers that we can use from D3. They are in the D3 array package. One is extent, which, given an array of numbers or whatever, it returns us the biggest and smallest value. And then there is D3 ticks that, given a start and stop, it gives us a value every count. The difference between doing it manually is that every value of ticks is already rounded and is super smart. So if you pass a date, it's going to actually be rounded to the date or to the hour, depending on the precision you require with count. So the way you use them is pretty straightforward. You import them, you pass extent, you pass your data and our accessor. For example, if we want to build our date access, our accessor function is going to return the date, which is a JavaScript date. And then we want to build 5 labels on throughout our axis. So we say tick from minimum to maximum 5 times. Done. If you want to see a code example of this, how it's actually implemented, we can see it here, which is going to be it was correct. It's going to be here. For example, this is the y-axis, and as you can see, I'm passing the data and the height of the chart and the margin. This is so we can correctly align the actual axis. I use the 3 extent on the data to get my minimum and maximum value. This is for the y-axis. The y-axis is the percentage of stress, so it goes from 0 to 100. I want to drive 5 points on my axis, so that's what I'm saying to ticks from 0 to 100 5 times. Then I create a linear scale for the y coordinates. That's exactly the same as in the chart. We could potentially also share it, but in this case, I'm going to make a new one. And in the render, we are rendering a div with some styling. The most important thing, of course, is the position absolute and the fact that it's aligning itself to the top plus the margin of the chart, to the left 0, and to the bottom 0 plus the margin. That way, our axis is in the correct position inside our container div. And then for every values, the one that we got from tick, we're just going to build, in this case, I decided to use a span with the actual value, which is a number. If we have a look at the example in the browser, okay, this doesn't work. How do I leave full screen now? Somebody knows the shortcuts to leave full screen? Okay. Well, what happened? Escape? No. It opens the console. let's make it in, here, there we go. Okay. It's not fun if you don't have some problems. So, if we see our axis is here on the left. No, sorry, wrong axis. Boom, here, there we go. We see that the height of the.
Can you reset the brackets application? Sorry.
Yeah.
No,
Oh.
the brackets application.
Oh.
Yeah.
What happened?
Pause and version. No, close and open again. Sorry.
How it's called?
Desktop, something desktop.
There we go. So here we see that our container div for the axis is perfectly fixed within the chart, and every span containing the value is in its correct position, because we are using the scale to decide on the y value of the axis. So. Once you have created your axes, you just add them at the bottom of your container div, passing it the properties they require here and there. And the basic of our line chart is actually already done. So we gain even more awesome things. Now we're using small isolated components for every part. The point is its own component, the tooltip is its own component, every axis is its own React component, and they are fully customizable. There is no limit, it's just standard DOM and SVG stuff. And then there is no magic involved. You're not relying on some D3 internal implementation. It's all simple React code you're already familiar with. So now let's add the animation to this chart. The first thing you should consider for the animation is a simple CSS transform, because simple is always better. In our case, we can use it in our tooltip. We just add a transform for the opacity. Simple opacity 250 milliseconds is in and out, and done. We have a nice animation for our tooltip, the transition. I didn't show you in the demo, but the tooltips are there. So. What about more complex animations, such as the line drawing animation or the points slowly appearing? Well, for that, D3 got your back. Let's have a look at some functions from D3 that I used for the specific animation you see in this chart. First is D3 timer. That's your best friend in this case. It's essentially a wrapper around the request animation frame of the browser, which is a function that you pass a callback, and that callback is going to be called as many times as possible to ensure 60 FPS. Why is it better than using request animation frame directly? Well, it's because the callback is past the currently elapsed time, and this becomes very handy. We will see why later. And then it has some other option like delay. For example, if you can say delay the start of this timer by 300 milliseconds. So what I'm doing for every point is the chart. Every point has a higher delay, and the D3 timer automatically starts the animation later. To stop the timer, you call the stop function on your timer. This is an example on how you use it. You define your duration, and when your elapsed time is greater than your duration, you just call the stop function on your timer. Next, let's look at the D3 ease package. Every function in the D3 ease package has the same, accept the same argument, which is a number from 0 to 1. And given that number from 0 to 1, it gives you another number from 0 to 1, which is the result of applying the ease function. For this demo, I used ease cubic in. Those images are directly from the D3 documentation, and ease cubic essentially has that shape. And then the other one I use is ease elastic, which has a nice shape. and it accepts some extra values like an amplitude and a period, and the image shows you how those two affect the result of the function. Lastly, we have D3 interpolate, which the definition is returns an interpolator between the two numbers a and b. I think this definition is too complex. I like it better. A magical mathematical device that when pass a number between 0 and 1 returns a corresponding number between a and b, which is exactly what I need. But if you're still like, what? Now that I know all these functions, how do I use them? Well, let's explain it this way. You have your timeline of your animation, of your duration, that goes from 0 to 500 milliseconds, right? Let's say we are 200 milliseconds into our animation. Then we need to project our 200 milliseconds as a value from 0 to 1, in a percentage essentially. In this case, it's 0.4. Then we want to apply our 0.4 to our is function. And in our example, it becomes 0.22. This is not mathematically correct. So I don't know, but as an example. And lastly, if we want to animate the radius of our circles, so our circles pop in, we simply project our 0.2 in a line that goes from 0 to 4 pixels, which is our ending radius of the circle. And we get back a value, 1.56 pixels. To see this in code, that's how we implement it. First, we start our timer, a duration of 1000 milliseconds. This code comes from the animation of the circles, by the way. So we have a duration of 1 second. We start our timer, and we stop our timer when the duration, the elapsed time goes above the duration. And we are at this stage, right? We're getting where we are in our timeline of the animation. Then we need a way to get the percentage of our animation, and a simple way to do that is to use a linear scale, where with the scale goes from 0 to our duration, and it's very important. The last properties you see, clamp, true. What that tells the linear scale is to never go above your final number of the range. In this case, because we did not specify it, by default, the range is from 0 to 1. So if we pass a duration, we pass a value that is above 1000, like 1200, it's going to still return 1. It's not going to go beyond 1. And this is important because maybe your D3 timer is called after 1 second passes. That's why to stop it, we check if the elapsed time is greater than the duration, because if there is some delay in the browser, your browser has been doing something else, your D3 timer is going to be called later. And that's why it's important that we don't go above 1 in our time scale. Then we apply our time scale to the elapsed time. And we end up in this stage, right, where we have our duration in milliseconds, and now we get back a percentage. Then that's where our is function comes in. In this case, we're using isElasticOut, passing those parameters. We feed our is function the previous number, and so we end up here. We now have a new value from 0 to 1. Lastly, that's where we use the interpolator. We want to interpolate for a radius between 0 and 4, so we create an interpolator, and we pass our interpolator our current time, which in this, and we get back the radius for our animation. And we end up at the last stage. So that's how we use those functions to orchestrate our animation. To actually put those animation into our chart, we need a last element, which is provided to us by React, specifically the React transition group. This is part of the official React repositories. You have two components, transition, and the transition you wrap around the element you actually want to animate. And then transition group, which you wrap all the children that you want to animate. So in a practical example, we wrap our point, our SVG circle, we wrap it into a transition component. And the transition component gives us a callback on enter. And on this on enter is where we start our D3 timer. When it fires on enter, we start our D3 timer and we start our animation. And we animate the circle radius using the state. Then in our line chart rendering function, we wrap the entirety of our points inside of transition group. It's important that we specify to render a G as a component, because by default it will render a div. And if you try to render a div into an SVG, your browser is not happy about that. So there we go. That's how you get 60 FPS in your chart. There is no hidden magic to it. Wait. That's all it takes. No specific optimization I had to do. And as you can see, this is the actual code, and it runs super smooth without any problem. If you want to have a look at the more complete code, it's basically, we can see it here. We are specifying the duration of 2 seconds. In the state, I'm saving the radius, start initializing it to 0. In our handle enter function, I will call the transition. And here we have our transition element that wraps the circle. The circle receives the radius from the state. And in the actual transition function, what I'm doing is taking the delay from the props. The delay, I'm passing it from the render of the line chart. And creating our timescale, the interpolator, the timer, applying the timescale and the ease function, and lastly getting the radius. Is exactly what you've seen before. And the delay will be decided inside of our render function, where depending on the current point, the point is decided upon the index of the actual point. So the farthest away are the points, the higher gonna be the delay. The other thing that I'm actually animating is the path, and the logic is here, but I will not show you that because it's a little bit cluttered because of the logic to toggle it on and off for the demo. So anyway, it's available in the repository for later if you want to have a look. Okay, but Alberto, does it scale? Does this approach actually work on bigger projects? And the answer is yes. Yes, it does. We had a chart 1.5 years ago at my company that it was built with D3 using the ref method, and every week there were a bug, there were a new problem with it. And fixing a bug just brought another bug because the code was a bit of a spaghetti mess due to using D3 with refs. Since the refactor is using this technique 1 year ago, there has been no bugs, none. It just works. So it does scale pretty well. There is a limit, but the limit is not with the technique itself, more with the browser. So earlier I showed you this pretty gigantic chart. The problem is that if I try to draw this as an SVG, there will be problems with the panning and zooming because the browser did not like to transform so many circles, so many SVG elements all at once. So instead, this example uses a canvas, and I will show you a bit of code from the actual production graph. It's similar to the original, sadly, similar to the original approach we saw in D3, where we are in the render, we're rendering an empty canvas with a ref attribute. I'm saving a reference of the canvas inside my component, and then I'm calling the drawing function for every node of the chart. There was another problem that for the pan and zoom action, if I had to save the new values of the position in the state, actually it will not go fluidly enough because all the lifecycle methods from React were actually slowing down the chart significantly. So what I had to end up doing is to, when I received from D3 the pan and zoom action, I saved the transform values as a property in our chart and directly called the draw graphs. This skips all the lifecycle events from React, and in this case, that made it way more performant. There are some other performance considerations you might want to take into account. The first is to always use the pure component. If you're not familiar with the pure component, it's exported in React. It's simply an alternative to the component that implements should component update. And that implementation of should component update avoids rendering your element again if none of the properties change. And this is shallow equality. So when you create your component, instead of saying class extend React, you can React.component, you can say extends React.pureComponent, and it will be the same. We've been using it everywhere, and we have not found a situation where it got in the way. The second thing is you should be careful of shallow equality. We will see more on this later. You should keep the render function lean and avoid computation in the render. Particularly if you are animating it, you need to keep in mind that now every render is actually your frame in the animation. So if you want to keep your animation 60 FPS, you don't have much time because you have maybe less than 16 milliseconds to perform the entire render functions. Why less than 60 milliseconds? Well, you need to account also for the React life cycles. So if you're lucky, you have 10, 11 milliseconds to render everything you need to. Otherwise, you're not going to hit 60 FPS. And then you should prefer small components, because if you have many small components, React is smart enough to only render the one that changed. And this will help you, particularly if you are animating. So let's have a look at better at this point. Be careful of shallow equality. So can anyone tell me what's wrong in this example? There is something that will get us many wasted renders. And the problem is here. Because we're doing this, our point element is going to receive a new function every time. And in JavaScript, a new function, even if it's the same function, is not shallowly equal. So because of this, the shallow equality check of our pure component is going to fail. And no matter that the data in the points did not change, this point element is going to render every single time. The way to fix this is pretty straightforward. We just pass the function directly, and it's going to be the job of the point to invoke those functions with the correct parameters. This is just an example of where you need to be careful of shallow equality. Another example is with arrays or objects. Every time you create an array in the render, that array, even if the content is identical, is not going to be shallow equal. So you're going to have many wasted renders. Your friends are immutable data structures. If you treat your data as immutable, you're going to avoid this problem of shallow equality. And that's it really. That's how you build charts in React the right way. So thank you.